Topics in the History of Mathematics, MA 290, Cassette 5, Side 2. Mathematics in 17th Century Holland. For this cassette we've travelled to Holland to talk with two academics from the University in Utrecht, Jan van Manen and Professor Klaus van Berkel, whose main work is at the Dutch Open University. Mathematics in 17th Century Holland. Klaus van Berkel, why should we be particularly interested in Dutch mathematics of this period?
Well, in the history of 17th century mathematics, very important developments took place in this country. We can, for instance, point to the following: the application of mathematics to physical questions, the quantifying of problems that had been treated in a purely qualitative way before. The creation of mathematical physics is not just a Dutch development, of course. Galileo in Italy, Mersenne in France, to name just two scientists, had their share in it. But it was Descartes who first published systematic treatises on mathematical physics, and he did it in Holland.
Jan van Manen.
Another important thing was that the geometry of Descartes was published in the Netherlands, and the first audience for Descartes' geometry was in the Netherlands. His main prophet, Frans van Schoten, worked there, and the fact that the geometry of Descartes spread so quickly through Europe was the main contribution of van Schoten. That's why mathematics in this period in the Netherlands is so important.
Politically, it was an interesting period in the history of the Netherlands as well, wasn't it, Klaus van Berkel? What was the situation at that time?
In Holland there was still a war going on against the Spanish king. In the beginning of the 17th century, this revolt had already resulted in a free and independent Dutch Republic. Although the war had not ended, it only ended in 1648 at the Peace of Westphalia, Holland and 6 allied provinces in the northern part of the Netherlands were internationally regarded as a new nation. But in a world dominated by kings and princes, it was a very strange nation indeed. The Dutch Republic was not ruled by a king, but by the Estates General, the representatives of the 7 provinces who regarded themselves as the true sovereign. William of Orange had retained his title of stadtholder to the king. The stadtholder is a direct representative of the king in the province, his lieutenant, you could say. But under the new republican circumstances, he was more of a servant to the states. And so was his son Maurits, stadtholder of Holland and some other provinces, and commander-in-chief of the Dutch army. But besides being a country with a federal constitution, dominated by merchants and patricians in cities, the Dutch Republic was also characterized by an unprecedented economic boom. Ships of the Dutch merchants were sailing all over the world, bringing in costly spices and raw materials from the Indies, from the Mediterranean, from the Baltic. In fact, Amsterdam functioned as a port of transshipment for the whole of northwestern Europe. It was not only commerce, however, that was blossoming. All over the country, but especially in the western parts, agriculture flourished and industry rose to prosperity. The money earned in commerce and industry was in part invested in large-scale enterprises and land reclaiming. It's good to remember that for all of these activities, mathematical skills were needed, and that the economic growth of the Dutch Republic was in part made possible by mathematical practitioners, like instructors of navigation, engineers, surveyors, and so on.
There were also some interesting social developments at this time, Jan van Manen.
In the beginning of the century, the Netherlands were marked, as Van Berkel already said, by the War of Independence against the Spanish king and the necessary construction of a proper economical, political and clerical system. The most important factor in this process was formed by the regents, the commercial upper class in the Dutch towns. There was no strong central administration, the nobility had little influence, and so the regents had every possibility to found new enterprises, which they did by making investments on a very large scale. Direct consequence of this development was the genesis of a large stream of practical mathematics, mainly arithmetic and geometry. The surveyor, mentioned already by Van Berkel, for example, was such a practical mathematician. He had a large supply of work. Towns were extended, new land was opened up, roads, canals and harbors were constructed. This process is reflected in a play of the famous Dutch playwright Bredero, written about 1610. At a certain point in the play, 2 people approach the city of Amsterdam. In the distance the city looms up, and one of the 2, the sly thief, remarks,
"How gloriously the city rises with all those new houses. The whole country, I hear, is packed with ditches and locks."
Between 1620 and 1650, several factors changed the character of mathematics in the Netherlands. Of course, there were influences that were common to all European mathematicians, such as the effects of new publications, of Viet, for example, of Descartes. Another factor was the coming into being of a new type of student. In the constructive period at the beginning of the century, study for most of the families, most of the merchant families, was a kind of investment which had to yield its profit. Shortly after having finished their studies, the students had to be productive and entered a job, often in the family firm. About 1650, however, the regent had established their position, and there was a considerable wealth in Dutch towns. And moreover, expansion of commercial activities had decreased, partly because of the competition with foreign economical powers. These changes in the economy resulted in a situation in which students more and more had a possibility to finance a long study period, often including an educational grand tour. And in this situation, subjects without a direct application to society could enter the program. Mathematics as a preliminary study for several other studies, and practical mathematics did not vanish, but a new interest in mathematics as an object of study in its own right supplemented the existing types. Most of the important Dutch mathematicians of the period around 1650, Huygens and Hudde for example, belonged to this new type of student. And a third factor was the growth of the number of students and of educational institutions. Between 1620 and 1650, a new university and several illustrious schools were founded.
And what about religious tolerance at the time?
Well, of course, the Dutch society is well known for its religious tolerance. Although the Calvinists had taken a great part in the revolt of the Netherlands, they were not able to establish their Reformed Church as this church of the state. They were privileged, of course, but Catholics, Lutherans, and Anabaptists were not forced to enter the Reformed Church. And all these characteristics of Dutch society, its federalism, its economic growth, its tolerance, were of importance for the intellectual life. For instance, to give just one example, it resulted in the foundation of no less than 5 universities in almost every province, universities with at least some degree of tolerance for dissenting views in faculties of philosophy, medicine and law, and especially the University of Leiden, the oldest one, had a reputation for tolerance in these matters.
Several now famous scientists and mathematicians travelled in Holland at this time. Can we look at the reasons why, for example, Descartes came to live here? First of all, put us in the picture about the dates and times of Descartes' stay in Holland.
Well, Descartes came to Holland for the first time in 1618, and he came back to Holland in 1628-29, and then he stayed there until 1649.
Why Holland?
Well, he came for several reasons. Let's look at the first visit to Holland in 1618. Descartes was disappointed in bookish learning and wanted to see something of the world, and that was a reason why he came to Holland, because there he thought a war was going on, and he hoped to be able to join the army of Prince Maurits, which had a French regiment. And so Descartes went to the city of Breda, in the southern part of the Netherlands, where a garrison was located. But there was not much war going on, and life in Breda proved to be rather dull. But then, late in 1618, something happened. This is what Descartes' first biographer, Daniel Lipstorp, tells us.
It happened that while Descartes was in Breda, a mathematician posed a problem for anyone to solve and put it up at some public place. Many passers-by gathered, including Descartes, but because of the fact that he'd come to the Netherlands so recently, he couldn't read the language. Therefore, he asked the man who was closest to him, and whom he later learnt was the famous Beckman, head of the Latin school at Dordrecht, and a mathematician of some merit, to translate it into French or Latin. Beckman did so, and urged Descartes to note down the problem and bring him the solution. Descartes didn't disappoint him, because when he got home, he solved it methodically. He did it just as quickly and with less trouble than Vieta had taken when he once solved in 3 hours a problem which Adrian van Roomen posed to all mathematicians of the world. After finding the solution, Descartes immediately went to Beckmann to keep his promise and show him his solution. From then on, Beckmann started to treat him with respect and to admire his talent, which was greater than he had thought.
Most of this story is fiction, serving two purposes. One is to extol the ingenuity of Descartes by showing how he outstripped even Vieta, and the other is to put Beckmann in his place as the inferior to Descartes. Many years after their friendly meeting at Breda, the two quarreled with each other about the intellectual ownership of some scientific discoveries, and Lipstorp, who was an adherent of Descartes, used the story to strengthen the case of Descartes. In reality, the meeting of Beckmann and Descartes had a very different character. From the scientific diary Beckmann kept since his study of mathematics and theology in the University of Leiden, we know how he and Descartes cooperated in finding solutions to well-known scientific problems. They discussed, for instance, problems in mathematics, mechanics, acoustics and hydrostatics, and in most of the cases it was Beckmann who posed the questions and gave a beginning of an answer. Most famous is their deduction of the law of falling bodies, a problem before them only solved by Galileo, but in a very different way. Descartes was very much impressed by the ideas and methods of Beckmann. When they parted just before New Year's Day 1619, Descartes gave his new friend a copy of his first scientific treatise, his Compendium Musicae. And in a letter some months later, he said to Beckmann,
"You were really the only one who roused me from my sleep. You brought to life all the learning that had almost vanished from my memory, and brought my talents back to more worthy business."
Descartes was not only impressed by Beckmann's ability to pose and answer certain scientific questions, but most of all by his way of dealing with these questions. Descartes told his Dutch friend how he had studied with the Jesuits, who were well known for their scientific knowledge. But, he added, he never had found someone who had combined physics and mathematics so accurately as Beckmann. And he was right. Beckmann was one of the first natural philosophers who developed something like mathematical physics. He had a strong conviction that all scientific problems could be dealt with by a combination of the mathematical and the physical, that is to say, purely mechanical properties of material bodies. For Beckmann, there was no reason to introduce occult qualities or real essences, like in the Aristotelian philosophy of nature. So, what he called his Philosophia Physico-Mathematica can also be seen as one of the first, not to say the first, manifestation of the mechanical worldview. And it is exactly this worldview, this mathematical way of dealing with physical problems, that stimulated Descartes to develop a scientific system of his own. Some 10 years after he had first visited the Dutch Republic, in 1628, Descartes once again came to Holland. This time his motivation was quite different from the first time. In Holland, Descartes now hoped to be able to work out his philosophical and scientific ideas he had developed in France. In Paris, with its demanding social life, he didn't find the rest to do his work, but in Holland, where he expected tolerance and a certain indifference towards strangers, the circumstances would be better. In a sense, he was wrong. Once he had published his ideas, some theologians and professors of philosophy protested against his so-called atheistic ideas, and an anti-Cartesian lobby, so you could say, in different universities tried to stop the spread of his ideas. But thanks to the fragmented federal structure of the Dutch Republic, no watertight measures were possible, and in Leiden and elsewhere, students could hear and read about what Descartes had discovered and thought out. In any case, his mathematics was completely left outside the discussion, and someone like van Schoten did not get into trouble with his Cartesian mathematics. On his way to Holland, Descartes visited his old friend Beckmann, who had by now become head of the Latin school at Dordrecht. Once again, Descartes had the opportunity to read in the scientific diary of his friend, and there he could read some very interesting ideas. The basic principles of Beckmann's philosophy of nature had not changed, but he had worked out his ideas in a much more concrete way. For instance, he had made a systematic study of the works of Johannes Kepler, the German astronomer. That's to say, not the mathematical part of his work, but the cosmological speculations in these books. Beckmann held Kepler in high regard, but his main criticism was that Kepler did not use mathematics enough. He deplored the fact, for instance, that Kepler had taken recourse to unexplained occult forces like the magnetical force, to explain the movements of the planets around the Sun and especially the three movements of the Earth. On the basis of his idea that everything in nature can be explained by taking into consideration the mechanical properties and the movements of unanimated material bodies, in his diary Beeckman had already constructed a hypothesis about small particles streaming from and around the Sun, moving the planets through space. And this hypothesis, he thought, could explain the actual movements of the planets without taking recourse to unknown forces. In conclusion, he noted,
In this way, I have proved that the three movements of the Earth are carried out without any fictitious internal force, and that they follow in a mathematical way from the movement of the particles that are transmitted from the Sun.
Well, Beeckman was so sure that his way was the right way that he considered a publication about this subject, just to prove that he could explain some things better than Kepler did. And in order to make such a publication possible, he started to reread and reorganize his diary entries on this subject. But in the end, all this came to nothing. Only after his death, a younger brother managed to publish an excerpt from the diary, which probably contained the notes Beeckman had already put aside for publication. That was in 1644. When this selection appeared, however, it was noted by contemporaries that there existed a great deal of resemblance between the ideas of Beeckman and the ideas on physics that Descartes put forward in his book The Principles of Philosophy in 1644, the same year. And in fact, it's undeniable that Descartes' physics is in large part stimulated by similar ideas of Beeckman. In fact, it may well have been the case that Descartes, shortly after his arrival in the Netherlands, abandoned his idea of working out his thoughts on method. The work later appeared as the Regulae, in part because of the fact that he realized that in case Beeckman would publish his book on cosmology first, he could claim priority for ideas that Descartes thought were his. This may well have been one of the reasons why Descartes started to work on a book called The World, finished in 1633. It was, however, the news of the trial of Galileo that kept him from publishing this book. He thought that the Copernican stand in it would harm its diffusion in Catholic countries. And that is why he once more decided to change his plans. Now he planned to publish a book on his methods after all, and this time he succeeded. In 1637, still without any mentioning of the name of the author, the Discourse on Method appeared with a French publisher in Leiden.
Jan van Manen, Descartes was the most important influence on mathematics in Holland, but it was because of Van Schroten that he had this influence, would you say?
Descartes was a kind of a god and Van Schroten was his prophet. I think that's the good metaphor. He was personally acquainted with Descartes already before the publication of the geometry. He was a great advocate of Cartesian mathematics and he taught it to famous students, like, for example, Christian Huygens. And by his books he influenced the leading mathematicians after his time, Newton and Leibniz and many others. Born about 1615, as the son of the professor at the Leiden Engineering School, he got a profound education in mathematics, which was extended during a visit to France, where he studied and collected texts of Viète and Fermat. In 1646 he succeeded his father at the engineering school and at Leiden University. His task there was to teach, but his main goal was to make the geometry of Descartes accessible to his fellow mathematicians. Van Schroten, in his preface to his Latin edition of Descartes' Geometry, said about it,
The geometry of Descartes could only be understood on its own by a few people, because of its learned conciseness and the difficulty of the questions that it deals with, and then only with careful attention and tireless labour. So there was a danger that readers, impatient with their labours, would abandon the arena because they either didn't know the goal or didn't recognise it despite their efforts. I knew that the author hadn't written it with the intention that anyone could grasp his method as easily as possible, but only to show some of the exquisite specimens of his method. So I thought it worthwhile to give advice to the public and to explain and illustrate the more difficult passages with plentiful examples.
His activities with respect to the geometry had two aspects, social aspects and aspects linked to the mathematical context of the geometry. Teaching, publishing, editing work of others, stimulating research of students and colleagues, writing letters, functioning as an intermediary, all these social activities made him the center of Cartesian mathematics in the Netherlands. As to the mathematical contents of van Schoten's work on the geometry. First of all, he translated it from French into Latin, which enlarged its audience greatly. Then he commented on Descartes' text. For example, he explained things, he filled in gaps, and he referred the reader to the literature. Then he systematized Descartes' incoherent thoughts, and finally he did a lot of exploring. He put new problems, he tested the theory on harder cases, and extended it. Let me give you one example. Descartes at a certain point in the geometry solves a geometrical problem. In fact, it is the problem of Pappus in 4 lines. Geometrically, the solution has to be a curve, but Descartes only derives its equation, and then he says, the curve is a parabola, and
It is easy to construct this parabola using the first problem from the first book of Apollonius's Conics.
the comment of van Schoten contains 17 pages in which he systematically adapts the ancient Greek theory of conic sections to the new analytic geometry. He takes his own problems in working through Descartes' geometry as a starting point and presents his solutions in his books. And in this case, his solutions resulted in the first systematical treatment of conic sections as part of analytic geometry. And finally, as to his explorations, van Schoten studied the problem how to draw conic sections with mechanical tools. And he stimulated his student De Witt, again a son of a regent, to give a classification of quadratic curves. Newton, in his formative period, was inspired strongly by these 2 studies, as he was by many more passages in van Schoten's books, which, in fact, were his first textbooks.
At the end of this period, there was a falling off in the interest and the level of activity. Can you say why that was or how it happened?
There were 2 factors that made the mathematics in the Netherlands go down at the end of the century. On the one hand, mathematicians thought that Descartes' geometry was the last word in its field. They thought that if you knew Descartes' geometry, you knew everything that there was to know. A second point is that the economy got worse at the end of the century, and there were military, political problems. The number of students, for example, decreased at the end of the century, and then the leading role was taken over by foreign countries.
Can you then summarize the importance of van Schoten?
To summarize the importance, you must go back to Descartes. Descartes wrote down a kind of a vision, an oracle about mathematics. Van Schoten, with his translation, his comments, his systematization and explorations, made mathematics out of it. And the main developments at the end of the 17th century, including the invention of the infinitesimal calculus, was founded upon this work of van Schoten. Van Schoten was the link between Descartes and modern mathematics. The mathematics we learn today are coming to us through van Schoten.
As we conclude this cassette on Dutch mathematics in the 17th century, Klaas van Berkel, could you explain the international influence of this period?
Well, just look at Christian Huygens. If there was an international figure in Dutch mathematics and science ever, it was Huygens, of course. Huygens is very important for the further development of mathematical physics, and he is, of course, a very important figure in the Cartesian mathematics developed by van Schoten and his circle. And in the work of Huygens, all this comes together. Say, for instance, in his work on the theory of light, which appeared in the time that Isaac Newton was already on the field. But Huygens is, of course, not just a Dutch figure of science, he's an international figure. He is on the same level as Newton and Leibniz, and that's where Dutch mathematics and the development of Dutch mathematics in the 17th century comes in the international scene.
Thank you very much, Klaas van Berkel and Jan van Manen.